Welcome to the next lecture on the course Descriptive Statistics with R software. You may recall that in the last two lectures we had discussed the concept of movements, and we discussed the raw movements, central movements and absolute movements. We also learned how to compute them on R software. Now I am going to introduce here the concept of skewness and kurtosis, which are again the two features of a frequency curve, and our objective is that to understand firstly what are these features, secondly how to quantify them, and thirdly how to compute them on the R software. When we are trying to quantify them, then you will see that we will need the definition of the movements, and in particularly the central movements. And that was the reason that I had explained those concepts earlier. So now let us start this discussion, and first we try to understand what is skewness. The dictionary or the literal meaning of the skewness is lack of symmetry. What does this mean? This symmetry is talking about the symmetry of the frequency curve or the frequency density. You had seen that how we have computed the frequency table. From there we had drawn the frequency density curve. So when we say that this is the lack of symmetry, then what is symmetry? Symmetry here is like this. So this is the basic meaning of symmetry. So now I am saying that this symmetry is lacking. When this symmetry is lacking, what will happen? Means in an ideal situation, if I say, suppose if I say this is my symmetry curve, then the symmetry is disturbed, means this curve will look like this, or this curve will look like this. Now, what is the interpretation of these curves? Suppose I try to take an example where we are counting the number of persons passing through a place where many offices are located. So we know what is the phenomena. The phenomena is like this, that usually the office will start at 9 o'clock, 10 o'clock in the morning. The traffic at that point will be very less, say around 7 AM, 8 AM in the morning. And then the traffic will start increasing, and then it will increase say up to 10 o'clock, 10:30 or say 11 o'clock in the morning, and after that the traffic will decrease. So in case if I want to show this phenomena through a curve, this curve will look like this. Suppose if I say this is the time here at say here 10 AM, and this is the time here somewhere here at say 7 AM, and this is the time here up to here say here 3 PM, say 10 AM, 11 AM and so on. And here is the number of persons passing through that point. So I can say here that from 7 AM this frequency or the number of persons, this is very small, it starts increasing, and then it keeps on increasing up to say 10 o'clock, and then after that everybody comes in the office, and then there are less number of people who are coming to office, and then finally see if you come up to here 3 PM, this number will decrease. Now on the other hand, the opposite happens in The third case, suppose if I try to mark these points as here as say 12 p.m., 1 p.m. and up to here sometime here, say here 6 p.m. and then here 7 p.m. and say here 9 p.m. and here we try to count the same record, same data, that is the number of person which is denoting the frequency. So, now what will happen once the office starts, and office is from say 9 to 5 or say 9 a.m. to 6 p.m. or so. So, usually in that marketplace or in that place where there are many offices, people will be working inside the office, and then in the evening when the office hours closes, then they will leave the office. So, what will happen? Say from say 12 o'clock or 1 o'clock, the number of person passing through that point will be very less, and this number will start increasing say from 4 p.m., 5 p.m. and it will be maximum say between say 5 p.m. and 6 p.m. and once everybody has left the office, then the number of person passing through that point will sharply decrease, and say at 7 p.m., 8 p.m. the number will be very less. So, now how to denote this phenomena through a curve? So, this type of phenomena can be expressed by this curve. So, initially at 12 o'clock the number is very less, and then say around 5 p.m., 6 p.m. the number is increasing, and then it is decreasing after say 7 p.m. or so. In both these cases, what is happening? You can see here more data is concentrated here in the first figure, and more data is concentrated on the right hand side in the last figure. So, these are the areas in red color where more data is concentrated. Now, if you try to take the third figure, you can see here in this case the curve is symmetric around the mid value. If you try to break the curve into two parts from this point, and if you try to fold it and if you keep it over this thing, then this will look symmetrical. So, what I am going to say, suppose the curve is like this, and if I try to break it in the mid and if I fold it, then the curve will look the same. So, this is what we mean by symmetry, and this feature is missing in the first and last curve. That if you try to break the first curve at this point and the last curve at this point where I am moving my pen, then this will not be symmetric. So, the objective here is how to study this departure from symmetry on the basis of given set of data. I would like to know on the basis of given set of data that whether the data is concentrated on the left hand side more or more concentrated on the right hand side of the frequency curve. So, this feature is called as skewness, and in order to quantify it we have a coefficient of skewness. So, now I can say that here skewness gives us an idea about the shape of the curve which is obtained by the frequency distribution or the frequency curve of the data, and it indicates us the nature and concentration of observation towards higher or lower values of the variable. So, you can see here I have plotted here three figures. I can call it say here figure 1, figure 2, and here this is here figure 3. So, I will call this figure number 3 as bell shaped curve. Why this is called bell shaped? Have you ever seen a bell? The bell is like this, and then there is here is a ring, right. So, you can see the structure of this curve here. This is symmetric. So, that is why this structure shape in the figure 3 is called as bell shaped curve. So, the bell shaped curve, I will say this is a symmetric curve. Now, when the symmetricity is lacking, then the frequency curve will look like as in figure 1 or figure 2. So, the curve is, or the frequency curve is more stressed towards right or towards left. This is indicating that more values are concentrated in this region in figure 1 and more values are concentrated in this region in the figure 2. In these cases, we say that the curves are skewed. So, a frequency distribution is said to be skewed if the frequency curve of the distribution is not the bell shaped curve and it is stressed more on one side than to the other. Now, how to identify it? Because now we have two types of lack of symmetry, one in figure 1 and one in figure 2. So, we try to give it here a name. So, let me rename the figure. This is figure 1, this is figure 2 and this is figure 3 from the last slide. So, now in the figure 1 you can see that the curve is more stretched on the right hand side. So, when the curve is more stretched on the right hand side, this is called as positively skewed curve. And similarly, if the curve is more stretched on the left hand side, then this is called as a negatively skewed curve. And in case of a symmetric curve, we assume that the curve is symmetric and we say that it has got 0 skewness. When we want to discuss the property of skewness, we try to write whether the frequency curve is positively skewed, negatively skewed or it is symmetric. And this is how we try to express the finding from the data. But definitely there will be one thing. Suppose if I try to take here two curves like this and like here this. Both the curves are positively skewed. So, the next question is, both the curves are positively skewed, but their structure is different. One curve is lacking the symmetry more than the others, but just by saying less or more, it will not help us. We need to quantify it. So, our next objective is that how to quantify this lack of symmetry. And in order to understand this thing, we have a concept of coefficient of skewness. And the definition of coefficient of skewness depends on the second and third central movements of the data. So, you may recall that we had denoted the second central movement by mu2 and third central movement by mu3. So, now the coefficient of skewness is denoted by beta 1 and this is defined as the square of third central movement divided by the cube of second central movement, and this is called the coefficient of skewness. There is another coefficient of skewness which is defined as the square root of this beta 1 and this is denoted by gamma 1. Now, what is the difference between the two measures of coefficient of skewness, that is beta 1 and gamma 1? You can see here that in the case of beta 1, mu3 can be positive or mu3 can be negative, but mu3 square will always be positive, and similarly mu2 will always be positive. So, mu2 cube will always be positive. So, this beta 1 will always be positive. So, this will give us the information on the magnitude of the skewness or the magnitude of the lack of symmetry, but this beta 1 will not be able to inform us whether the skewness is positive or negative. Whereas, when we are trying to use the next coefficient gamma 1, then what we try to do here, that gamma 1 will also give us information about the sign, and when I try to combine the information obtained by beta 1, then this gamma 1 will give us the information on the magnitude as well as the sign. Sign can be positive, sign can be negative, indicating the positive or negative skewness. So, this is the basic difference between the two measures beta 1 and gamma 1, and you will see that in the R software provides the value of gamma 1. And one thing now you have to notice here, well, I can explain you on this slide itself, that I have defined here beta 1 and gamma 1, this is for the population. But what happens to us? We have got a data set, say x1, x2 and here say here xn. In this case, what we try to do? We try to compute the value of mu2 and mu3 on the basis of data x1, x2, xn, or they are called as sample movements. So, we try to compute the sample movements of order 2 and 3, and we try to replace mu2 and mu3 by their sample movements. So, in this case, this beta 1 I am trying to denote it by beta 1 s, that means beta 1 based on the sample values becomes like this. So, that is the same thing. I simply have computed the second and third central movements and I have replaced it in the definition of beta 1. Next, the coefficient of gamma 1, now I am denoting by gamma 1 s, s means sample, this becomes here the square root of beta 1 s, and it is given by here like this, simply the square root of the beta 1 s. So, now this will give us the information on the magnitude and sign, and whereas beta 1 will give us information only on the magnitude. Now, what is the interpretation? The interpretation goes like this. So, I am trying to divide the interpretation based on gamma 1 and gamma 1 s, and both are actually the same. So, the first case is, if I say gamma 1 is equal to 0, this means the distribution is symmetric. When I say gamma 1 is greater than 0, that is positive, then the distribution is also said to be positively skewed. And if gamma 1 is negative, then the distribution is negatively skewed. And the same continues for the definition of gamma 1 s. If gamma 1 s is 0, this means symmetric. If gamma 1 s is positive, that means the distribution is positively skewed. If gamma 1 is negative, then the distribution is negatively skewed. So, you can see here now that having the coefficient of skewness, it is not difficult to know the feature of the frequency curve with respect to the symmetry, and I can say whether my distribution is symmetric or not. If not symmetric, then it is positively skewed or negatively skewed. Now, a simple question comes, what happens to your here mean, median and mode in these different types of distributions when the distribution is symmetric or positively or say negatively skewed. So, now I try to give you a brief information. When we have a positively skewed distribution, in this case gamma 1 will be equal to 0. Now, if you recall, what will be the here mode? Mode will be somewhere here, which is the maximum frequency value. So, corresponding to maximum frequency, this will give me the value of here mode. Median is the value which will try to divide the entire area under this curve into two parts. So, this will be somewhere here, and the mean will be somewhere here. So, in the case of positively skewed distribution, mode will have the highest value followed by median and mean. So, mode will be smaller than median and median will be smaller than mean. The opposite will happen when we have the negatively skewed distribution. In this case, the mode will be somewhere here corresponding to this frequency. So, mode will be somewhere here corresponding to x, and similarly the median will be corresponding to this frequency and median will be somewhere here and the mean will be somewhere here. So, in this case, when we have the negatively skewed distribution, then mode will be greater than median and median will be greater than mean. Whereas in the case of symmetric distribution, all the values of mean, median and mode, they are going to be the same, see here, and in this case gamma 1 is equal to 0 and median, mean, median, mode will be somewhere here. There are some more coefficients of skewness which have been given in the literature. So, I will just briefly give you an idea. So, one measure of coefficient of skewness or one coefficient of skewness is based on the mean and mode, which is given by mean minus mode divided by standard deviation. So, sigma x is giving the value of standard deviation. So, this is essentially the value of say S what we have used in the earlier lecture, but I am using here is say here sigma x just to denote it that this is standard deviation, because that is the standard notation in many books, and this is the same as this quantity which is based on the mean and median, because you may recall that we have a relationship that x bar minus mode is approximately equal to 3 times x bar minus median under certain conditions. So, these two measures lie between -3 and +3, and we say that if these coefficients are greater than 0, that means the curve is positively skewed. If they are negative, that means the curve is negatively skewed, and if this coefficient is 0, that means the curve is symmetric. And similarly, we have two more measures which are based on the definitions of quartiles and percentile. So, the coefficient of skewness based on quartiles is given by like this Q3 minus Q2 minus Q2 minus Q1 and divided by Q3 minus Q2 plus Q2 minus Q1. And similarly, the coefficient based on percentile is given by this formula, and both these coefficient they lie between -1 and +1, and they have the same interpretation as earlier. Means positive value of this coefficient will indicate positively skewed curve, negative value will indicate the negatively skewed curve, and 0 value will indicate the symmetric curve. Now, after this I come on the next aspect, which is called kurtosis. Please try to observe here in this picture. I have made here 3 curves. The curve in the cell, let me call it here curve 1, 2 and here 3. I request you please try to observe the hump of the curve. Where is the hump of the curve? Which is here. I am making it by yellow color. This. And by looking at these 3 curves, can we really say that what is the feature related to the peak of the curve? The peak of the curve 3, this is the highest, followed by the peak of the curve number 2 and followed by the peak of curve number 1. So, the question is how to show this property of peaks and how to quantify it. So, this property of kurtosis, this describes the peakedness or flatness of a frequency curve. Flatness means how flat is the curve at the peak. Now, after this you can see here from this curve that one of the curve has more peak and other curves have less peaks. But how to compare it? What is more and what is less? So, what we try to do here, we try to measure the peakedness with respect to the peakedness of normal distribution. What is the normal distribution? In statistics, we have a probability density function, what we call as normal distribution, or sometimes it is called as Gaussian distribution. So, before I try to give you an idea about this peakedness, let me try to give you the idea of normal distribution. So, the probability density function of a normal distribution function is given by like this, and this probability density function is controlled by 2 parameters, mu and sigma square. So, we denote this function as say here n, which means normal, and the two parameters mu and sigma square, which are the parameters of this density function. Here this mu is indicating the mean and sigma square is indicating the variance. So, if I try to draw this curve, this will look here like this. So, this value is indicating here the mean, and this spread here around the mean, this is giving us the value of sigma square. And this curve is actually symmetric around mean. So, we try to compute the coefficient of skewness and kurtosis in the case of normal distribution, and in this case the coefficient of skewness comes out to be 0 and coefficient of kurtosis comes out to be 0. And this was the reason that we were trying to conclude on the basis of coefficient of skewness being 0, positive or negative. And similarly, we are going to do with the case of kurtosis. So, now the curve of the normal distribution will have 0 kurtosis. So, now we can compare the peaks of other curves with respect to the normal curve, and this is what we are doing in this picture. Here if you try to see the curve in the mid, curve number here 2, this is the curve of normal distribution, and we are trying to compare the flatness or peakedness with respect to the curve number 2. So, now you can see here first into the curve number 3, this is here, which is here. The curve number 3 has got more peak than the curve number 2, and similarly if you try to look in the curve number 1, then curve number 1 has got a smaller peak than the curve number 2. So, what we try to do here, that all those curves which have got higher peaks than the normal curve, they are called as leptokurtic. The peakedness of the normal distribution is called as mesokurtic, and the peakedness of those curves which have got lower peak than that of normal curve, this is called platykurtic. And this is how we try to characterize the less or more peakedness with respect to the peakedness of the normal distribution or the mesokurtic curve. So, now I can explain you that the shape of the hump, which is the middle part of the curve or the frequency distribution of the normal distribution, has been accepted as a standard one. And this kurtosis, the property of kurtosis, examines the hump of, or the flatness of the given frequency curve or distribution with respect to the hump or flatness of the normal distribution, which we have just understood. And those curves which have got the hump like a normal distribution, they are called mesokurtic. Curves with greater peakedness or say less flatness than that of normal distribution curve, they are called as leptokurtic curves. And those curves which have got less peakedness or say greater flatness than that of normal distribution, they are called as platykurtic curves. Now, the next question is how to quantify it. So, we have a coefficient of kurtosis, and there are different types of coefficient of kurtosis, but here we are first going to consider the Karl-Pearson's coefficient of kurtosis, which is denoted by beta 2. That is the standard notation. And similar to the coefficient of skewness, you can see here that this beta 2 is also depending on the mu 2 and mu 4. What are this mu 2 and mu 4? Mu 2 is the second central moment and mu 4 is the fourth central moment. And the coefficient of kurtosis is defined as the fourth central moment divided by the square of second central moment. The value of beta 2 for a normal distribution, this comes out to be 3. So, what we try to do that we try to define another measure which is beta 2 minus 3 and we denote it by here gamma 2. Now, the advantage of gamma 2 is that just by looking at the value of gamma 2 we will get the idea of the magnitude, and if this is greater than 0, smaller than 0 or equal to 0 will give us the idea about the nature of hump. So, that is why we have two coefficient of kurtosis, and in our software this gamma 2 is produced in the outcome. So, now you can see here the same thing. So, I can say here for a normal distribution beta 2 is equal to 3 and gamma 2 equal to 0, and if beta 2 is greater than 3 or gamma 2 is greater than 0, then we say that the curve is leptokurtic. If beta 2 is equal to 3 and or equivalently the gamma 2 is equal to 0, then we say the frequency distribution or the frequency curve is mesokurtic, and if beta 2 is smaller than 3 and gamma 2 is smaller than 0, then we say that the distribution is platykurtic. So, you can see here that in the same figure that we had drawn for the curves leptokurtic, we have this, for mesokurtic we have this, and for platykurtic we have this. So, this is about the coefficient of kurtosis. Some properties which I am not going to prove here, it is just trying to say that beta 2 the coefficient of kurtosis will always be greater than or equal to 1, and coefficient of kurtosis beta 2 will always be greater than the coefficient of skewness beta 1, and this beta 2 will always be greater than or equal to beta 1 plus 1. These are some properties just for your information, I am not going to use it here, and but I would try to define the sample based coefficient of kurtosis, because there in the beta 2 and gamma 2 I simply use the population values. So, now I know I do not have to do anything, I need here two central movements mu 2 and mu 4. I will try to compute the sample based movements, that means the value of mu 2 and mu 4 on the basis of given set of data, and I will simply replace them in the coefficient of kurtosis, and I am denoting this coefficient of kurtosis as beta 2 s, right. S means sample, and similarly the coefficient of kurtosis gamma 2 is now transformed to gamma 2 s, and this is the same thing beta 2 s minus 3, and they have the same interpretation as we have the case in the beta 2 and gamma 2. For leptokurtic distribution beta 2 s and gamma will be greater than 3 and gamma 2 s will be greater than 0. Similarly, beta 2 s will be 3 or gamma 2 s will be 0 in case of mesokurtic, and beta 2 s will be smaller than 3 or gamma 2 s will be smaller than 0 in case of platykurtic distribution. Right. So, now we have a fair idea that how to measure two types of characteristics in a frequency curve, what is the symmetry and other is the peakedness, and they are going to be quantified by coefficients of skewness and kurtosis. So, now the next question is how to compute them in the R software. So, as we have seen that in the case of computing the movements we need a package movements. So, obviously, in order to compute the coefficients of kurtosis and coefficient of skewness we need the information on the movements mu 2, mu 3 and mu 4. So, we first need to install the package movements, and then based on that we can compute the coefficient of skewness and coefficient of kurtosis. So, we try to understand it here. So, in order to compute the coefficient of skewness and kurtosis in R, first you need to install the package movements by this command install dot packages. Inside the arguments you have to write movements, and then you have to load this package movements, right. And now the sample based coefficient of kurtosis, which was our gamma 1 s, this will be computed by the expression skewness SKEWNESS and the data vector here x. And if you want to use the na dot rm, which means for the missing value you are saying this is here false. That means there are no missing values, and if there are missing value we will simply write na dot rm is equal to true. And similarly, the sample based coefficient of kurtosis, which we have defined as gamma 2 s, this will be computed by the command kurtosis KURTOSIS all in small letters, and inside the argument same thing like the data vector x, and if you do not have any missing value, then use na dot rm is equal to false, and if there are missing values, then use na dot rm is equal to true. Okay, so you can see here this is not a difficult thing. So yeah, if you have missing values and if you try to store those missing values inside the data vector xna, then the command will become skewness xna and na dot rm is equal to true for computing the coefficient of skewness, and the coefficient of kurtosis in this case will be given by kurtosis x dot na and na dot rm is equal to true. Right. Now, I will try to take an example and show you that how to measure this skewness and kurtosis in the data. So, I am going to use the same example in which we had collected the timings of 20 participants in a race, and this data has been stored inside a variable say time. Now, after this we simply have to use the command skewness skewness, and inside the argument give the data vector, and this is giving us the value 0.05759762. So, this is indicating that the skewness is greater than 0. So, the frequency curve in this case is positively skewed. And similarly, you can see here when you try to operate the kurtosis command on the time vector, then it is giving you the value 1.7 and which is greater than 0. So, this is indicating that the curve is leptokurtic. Leptokurtic means the hump of this curve is greater than the hump of normal distribution. Now, I will try to show you it on R software. So, you can see here I have here the data on time. First I need to load the package library moments, and I already have installed this package on my computer. So, now I will need the skewness of time, this comes out to be like this, and kurtosis of time. Right, you can see here this is the same thing which you have just obtained, and this is the screenshot of the same operation that I just did. And now I will take one more example where I will show you that how to compute the coefficient of skewness and kurtosis when we have some data missing. So, I will take the same example in which I have just removed first two observation and I have replaced it by na, that means the data is missing, and this data is stored in the data vector time dot na. And now I will use the command skewness on time dot na with the option na dot rm is equal to true. That means, please remove the na value and then you try to compute the skewness. And similarly, for the kurtosis, I will use the same command kurtosis on the time dot na with an option na dot rm is equal to true, and this will give me the value of coefficient of kurtosis when the two values are missing. So, now you can see here the coefficient of skewness comes out to be negative, this is less than 0. So, that means the frequency curve based on the remaining observation is now negatively skewed. So, this is indicating that when the first two observations are deleted, then the nature of the skewness has changed. Similarly, for the kurtosis, this value is 1.81 which is greater than 0. This is again showing that the curve is leptokurtic. So, this is indicating that even after removing the first two observation, the nature of the curve remains the same. And now I will try to show you this on the R software also. So, I already have stored this data time dot na on my computer. This is like this. Now, I want to compute the skewness. This is coming out to be the same what we have just observed, and if I want to compute the coefficient of kurtosis, this is here like this. And then the next slide is the screenshot of the same operation that we have done. Now, I would stop in this lecture, and you can see that we have discussed the coefficient of skewness and kurtosis, which are going to give you two more pieces of information about your frequency curve beside central tendency and variation. Now, you know how to find the behavior of the frequency curve with respect to central tendency, variation, lack of symmetry and peakedness. And now you can see, just by looking at the data, you were not getting all these things, but now you know that how to quantify these things and how the graphics in this case will look like. Means if you try to plot the frequency curves of the data which I have taken, say time or say time dot NA, and try to see whether the feature of the curve is matching with the information given by the coefficient of skewness and kurtosis or not, and you will see that it is matching. So, this is the advantage of these tools of descriptive statistics, that instead of looking at the huge data sets, you simply try to look into these values graphically as well as quantitative way, and they will give you a very reliable information. But you should know how to use this information and how to interpret the data. So, now up to now from the beginning I have used the tools when we have data only on one variable. So, we have discussed the univariate tools of descriptive statistics. Now, from the next lecture I will take up the case when we have more than one variable, and in particular I will consider two variables. So, when we have the data on two variables, they also have some hidden properties and characteristics. So, how to quantify them and how to have the information graphically. These are the topics which I will be taking from the next lecture. So, you practice these tools, try to understand it and enjoy it, and I will see you in the next lecture. Till then, goodbye.